Starships in movies glide through empty space like it's an ocean of nothing. In reality, the gap between stars is a high-speed minefield of dust, radiation, and invisible particle beams that rip real hardware apart. In this video, we're going to walk through the hard physics of why a human crewed starship that actually survives interstellar travel isn't just hard, it's almost completely crushed by the universe's own rules. You've heard space is a vacuum your whole life. Technically that's true compared to air, but it's also a kind of marketing lie. Even in the empty space between stars there's gas. In the interstellar medium you're flying through roughly 1/10 to 1 hydrogen atom in every cubic centimetre. That's the volume of a sugar cube. Spread those atoms out into a cubic metre and you get up to about 1,000,000 atoms in that metre. 1,000,000 atoms per cubic metre sounds tiny until you look at the distance you want to travel. Take a nearby star around 4 light years away. That's about 4 times 10 to the 16 metres, around 40 trillion kilometres, roughly 25 trillion miles. If your starship has a frontal area of about 100 square metres, say a rectangle 10 metres by 10 metres, that nose sweeps through a volume of space equal to that area multiplied by that distance. You're talking around 4 times 10 to the 18 cubic metres of space just for a one-way trip to the closest star. Now combine those two things. Up to 1,000,000 atoms per cubic metre multiplied by 4 billion cubic metres of path means you plough through something like 10 to the 24 atoms, 1,000,000 billion hydrogen atoms smashing into your ship. That's just the gas. That's with empty space. Space is thin, but the distance is so huge the total number of collisions is brutal. Gas alone is annoying, but maybe not fatal. The real problem shows up when you stop talking about single atoms and start talking about dust. Only about 1% of the mass in the interstellar medium is dust. But dust grains are many orders of magnitude bigger than single atoms, and their impacts are the ones that matter for survival. These grains range from micrometers, like smoke particles, up to millimeters, like fine sand. Take a grain around 10 micrometers across, roughly 1/10 the width of a human hair. It might have a mass around 1/trillionth of a kilogram. That still sounds tiny, but now give it a speed of 1/10 of the speed of light, about 30,000 kilometers per second, roughly 67 million miles per hour. At that speed, the energy carried by that single tiny grain is in the same ballpark as a rifle bullet hitting you. We already see the low-speed version of this problem in Earth orbit. Spacecraft that come back from a few years in low Earth orbit, flying at about 7 to 8 kilometers per second, show pits and scars from micrometeoroids and debris. Some of that junk hits at around 10 kilometers per second, about 22,000 miles per hour, and it still chews up metal surfaces. Now scale that speed up by a factor of 3,000. At that point, dust is not dust in the everyday sense. It behaves like high-energy projectiles. You might want to say, fine, but dust must be incredibly rare out there. That's where long distances crush your optimism. Go back to that 100 square metre ship nose and that 4 light-year trip. The path volume we talked about, around 4 times 10 to the 18 cubic metres, is huge, even if there's only one dangerous dust grain in every 1,000,000 cubic metres, which is a very low estimate. You still hit about 4 trillion grains on the way. 4 trillion high-speed dust grains is not a cosmetic issue. Each impact is a tiny violent event, and they keep coming second after second for decades. The front of your ship isn't just getting scratched, it's being ground down. Surfaces erode, thin parts get thinner, and some fraction of those hits land on places you really care about, like structural supports, fuel lines, radiators, or sensor systems. You're not designing for maybe we'll get hit once. You're designing for we will be hit again and again in every square centimetre over the whole trip. On Earth, you're protected from this kind of constant high-velocity bombardment by the atmosphere, and that protection is easy to underestimate. When small rocks and dust come in from space, they slam into thick air, get compressed, heat up, and usually burn up as meteors. You see a quick streak of light and then they're gone. The air slows them down and spreads their energy out before they ever reach the ground. In interstellar space, you don't have that help. There is no air, no thick blanket of gas, nothing to gently slow grains down before they hit. So every collision happens at full speed. A grain doesn't lose energy before impact, it dumps almost all of it right into whatever part of your ship it hits. There's no natural shield in front of you unless you bring it with you. And bringing your own atmosphere in the form of shielding means adding a lot of mass. This leads straight into a hard break with the way starships are usually drawn. Those sleek ships with big glass windows at the front, thin panels and delicate antennas pointing forward do not survive this environment at a tenth of light speed. Anything fragile facing the direction of travel gets cut off, shredded or vaporized. It's not about style, it's about simple survival over decades in a constant storm of high-speed particles. So to have even a small chance of reaching another star in one piece, you're forced toward a very different kind of design. The front of the ship has to be heavy, thick, and extremely tough. You need real armor, maybe several meters of dense material, and all the critical stuff has to hide behind it. Sensors have to peek out from protected spots, not sit exposed on stalks. Habitats, fuel tanks, reactors all get buried deep in the shadow of that armoured nose, but the moment you start adding serious armour, you hit another wall. Thick shielding means huge mass, and huge mass makes it almost impossible to accelerate to those same high speeds with any rocket system we understand. You fix the space is not empty problem only by creating a propulsion and energy problem that is just as bad or worse. And we haven't even talked yet about how those dust impacts actually behave at these speeds on the microscopic level. Because at a tenth of light speed and above, collisions stop acting like normal impacts altogether. The dust doesn't just chip your hull, it turns into explosive plasma that can punch far past the surface and blow chunks out from the inside. When you see what a single grain does in that regime, the idea of surviving trillions of them stops looking hard and starts looking basically impossible. So how bad is one of those tiny grains, really, when it slams into your ship at a tenth of light speed? At that point, the word impact stops meaning what you think it means. You're not dealing with dents and craters, you're dealing with matter turning straight into plasma. At around a tenth of the speed of light, close to 30,000 kilometers per second, roughly 67 million miles per hour, the energy in a moving object scales with the square of its speed. Double the speed, you get 4 times the energy. Multiply the speed by 1,000 or more, and the energy per kilogram goes up by 1,000,000. A dust grain weighing about 1 milligram, something you could barely see on your fingertip, carries, at those speeds, many times the energy per kilogram that you get from high explosive. Per kilogram, it beats TNT by tens of times, so even that tiny grain is effectively a microscopic-shaped charge, a focused blast, pointed exactly into the direction of your flight. When it hits your hull, the grain and part of your armour don't gently deform, they vaporize into an ultra-hot, ultra-fast cloud of ionized gas. That cloud then bores further into the material like a cutting torch that appears out of nowhere for a fraction of a second. That's not just theory. There are experiments on Earth that show the start of this behaviour, at far lower speeds. So what do those real tests tell you about what happens when you crank the speed up by thousands of times? In labs, we already fire tiny projectiles at 10 to 15 kilometers per second, something like 22,000 to 34,000 miles per hour into metal plates. Those speeds are similar to the faster bits of orbital debris near Earth. Even there, at only a tiny fraction of light speed, the impacts are nasty. The projectiles don't bounce, they punch neat holes, carve out craters, and spray clouds of molten and vaporized metal out the back. That's why the International Space Station does not rely on a single metal wall. It uses multi-layer Whipple shields, where a thin outer plate breaks the projectile into a cloud and then inner layers, spaced a few centimeters apart, spread and absorb that cloud before it reaches the pressure hull. Those systems are designed to handle pieces a few millimeters across at around 10 kilometers per second. Now compare that to what you're asking of an interstellar ship. You want to survive impacts at 2,000 to 3,000 times that velocity. The energy per kilogram goes up by a factor of millions. Physics does not get kinder as you go faster. All the ugly behaviours you see in those hypervelocity tests, the holes, the sprawl, the melting get amplified. The lab shots are already at the edge of what current materials can take. At 1/10 of light speed, you are far beyond that edge. And the hit is not just about the spot where the grain lands. The whole structure around it gets dragged into the event. So what happens deeper inside your material when a hypervelocity impact lands on your armour? When a grain slams into the hull at that speed, a violent shockwave explodes outward from the impact point, racing through the material faster than sound in that metal or composite. That shock compresses, stretches, and twists the structure as it moves. On the front side, you see a crater or a hole. On the back side, something worse can happen: spallation. That's where chunks of material, sometimes thin layers, sometimes big flakes, break off and fly inward. The material is effectively torn apart from inside by tension as the shock reflects off the far surface. So a single unlucky grain hitting what looks like a thick, solid plate can send fragments shooting off the back toward whatever you are trying to protect. Tanks, cabling, habitat walls. The shock can also start cracks in beams and joints. At low speeds, you might call this minor damage. At 1/10 of light speed, where the energy is huge, those cracks can grow, link up, and travel along structural members. One random grain can turn into a mission-scale problem because it has just weakened a major support, or opened a leak in a critical line, or shaken a sensitive system out of alignment. Now look at the temperature side of this. Turning solid matter into plasma is not a gentle process. What sort of heat are you dumping into your armour at every hit? At the impact point, the grain's kinetic energy is dumped into a tiny volume in an incredibly short time. That region heats to tens of thousands of Kelvin, easily hotter than the surface of the Sun, which is under 6,000 Kelvin. At those temperatures, atoms are stripped of their electrons. You get a burst of plasma punching into your ship, not just hot gas. That plasma radiates across a wide spectrum, including X-rays. It throws out secondary particles that can penetrate deeper than the initial crater. Anything nearby that doesn't like high temperature or ionizing radiation is now in trouble. Sensors, cameras, radar dishes, wiring, electronics, optical fibers, all of that hardware can get fried by one close-range hit. Semiconductors can be damaged permanently. Insulation can char or outgas. Even if the armour survives in the sense that it doesn't fully puncture, the systems you need to steer and monitor the ship can be wiped out by repeated bursts of radiation from these micro-explosions. So now you're not just armouring against holes, you're trying to harden everything against random, localised, star-hot flashes chewing through your front end. If this were a freak event, like a once-per-mission nightmare, you could maybe accept the risk. But over interstellar distances and decades of travel, it doesn't stay rare. So how often are you actually taking these hypervelocity hits? Over a path of several light years, with even conservative dust densities, the number of high-energy impacts on a 100 square metre nose runs into the trillions. They're not all the same size, most are small, some are much larger, but the key point is this: the count is huge and the rate is steady. You're not designing a ship to survive a single collision and then retire. You're designing a ship that must take an almost continuous stream of explosive micro-impacts year after year, without losing structural integrity, without losing critical systems, and without cooking its own electronics. That essentially forces you into only one direction: extremely thick, extremely robust shielding on the front, not centimetres, meters. Layers of sacrificial material that can be chewed away over time, with more layers behind that. But the more layers you add, the more mass you pile on. That mass has to be pushed to 1/10 of light speed, then slowed down again at the destination, and maybe even turned around if you ever want to come home. And that takes you straight into the next hard wall. Thick enough shielding to survive the dust turns your starship into something incredibly heavy. Moving that mass to interstellar speeds demands energy and fuel on a scale that even a planet-wide civilization would struggle to provide. You've solved one problem, at least on paper, but you've walked directly into another one that is just as unforgiving. The mass and energy trap that makes a truly survivable high-speed interstellar ship look less like a vehicle and more like an engineering contradiction. Here's the trap you hit the moment you try to make your Starship actually survive those dust impacts. Instead of just hoping they won't happen, you already know thin metal walls are useless at 1/10 of light speed. So the obvious answer is, fine, we'll add better shielding. That sounds reasonable. Then you run the numbers and the whole design blows up in your face. Right now in low Earth orbit, the International Space Station deals with debris hitting at around 10 kilometers per second, roughly 22,000 miles per hour. To handle that, it uses Whipple shields, a few centimeters thick. There's a thin outer bumper, some space, then the real pressure wall. When a small piece of junk hits, it shatters on the bumper, spreads out into a cloud, and the inner layers absorb that cloud before it reaches the astronauts inside. For that environment, for those speeds, a few centimeters of aluminum and special fabrics do the job. Now jump from 10 kilometers per second to 30,000 kilometers per second, about 67 million miles per hour. The speed is 3,000 times higher, but energy goes with the square of speed, so the impact energy per kilogram goes up by a factor of around 10 million. Scaling laws and impact studies tell you something harsh. You're no longer talking about centimeters of protection, you're talking about meters. Several meters of dense material in front of every critical system just to have a chance of stopping or at least spreading out those hypervelocity grains. So instead of a thin metal skin, you end up with a shield 5 to 10 meters thick. Basically a solid block of armor on the nose. 5 meters is over 16 feet, 10 meters is over 30 feet. That's like strapping a 3-story building across the front of your ship with everything important hiding in its shadow. And that's only for the forward direction. Any part of the ship that sticks out into the wind gets its own problem. So what actually happens to your ship's mass when you bolt that kind of armor onto the front? This is where the numbers stop being just big and start being absurd. Take a reasonable starship. Say the dry mass, without fuel or shielding, is about 1,000 tons, so 1,000,000 kilograms. That's already a lot, about the mass of a large ocean ship or a tall building. Now you add a shield 5 meters thick over an area of 100 square meters on the nose, about a 10 by 10 meter square. If you build that shield out of steel, which has a density around 8,000 kilograms per cubic meter, the volume of the shield is 500 cubic meters. Multiply that by 8,000 and you get about 4 million kilograms. So the shield alone weighs roughly 4,000 tons. That's 4 times more than the rest of your entire ship. You just turned a 1,000-ton craft into a 5,000-ton monster, and that's only counting the front shield, not side protection, not internal reinforcement, not extra structure to hold all that weight in place during thrust. Now, ask what that does to your propulsion. If you want to reach the same top speed in the same time, with 5 times the mass, you need roughly 5 times the thrust and roughly 5 times the energy. If you're using rockets that carry their own propellant, it gets even worse, because adding mass on the front forces you to add even more mass in fuel tanks and engines to push it. Your fuel needs start to explode much faster than your payload grows. There's a simple law behind this, the rocket equation, and it absolutely does not care about your feelings or your sci-fi dreams. The change in speed your rocket can achieve depends on 3 things: how fast your exhaust shoots out this back, how strong gravity is, and the ratio between your starting mass and your final mass after the fuel is burned. The key detail is that this relationship uses a logarithm. That means every extra chunk of speed you want costs you more and more fuel, and every time you make the ship heavier, the fuel requirement doesn't just go up in a straight line, it grows exponentially. Chemical rockets like the ones we use now can give a specific impulse of around 450 seconds. That's already barely enough to reach low Earth orbit at about 7.5 kilometers per second. To get anywhere near 1/10 of light speed, 30,000 kilometers per second, you need changes in speed that are thousands of times larger. Even if you jump to nuclear thermal rockets, maybe 900 seconds, or even very optimistic ion drives at around 3,000 seconds, the math still slams you. The heavier your shield gets, the worse the starting mass to final mass ratio becomes. You end up needing ridiculous amounts of propellant. Most of your ship becomes fuel tanks, and your Starship shrinks to a tiny protected payload glued to the front of a flying fuel mountain. So maybe you try to dodge the fuel problem entirely. Don't carry propellant, just push the ship with external power. Does that actually fix anything, or do you just move the impossibility somewhere else? Beamed power and light sails sound like the escape hatch. Put a huge, ultra-thin reflective sail on the front or back of the ship, shine a massive laser or microwave beam from your home system, and let photon pressure slowly push you up to interstellar speed. Now your ship doesn't drag around thousands of tons of fuel, so you've beaten the rocket equation, right? Not really. You still have the mass of the ship and the shield, and a heavier object takes longer to accelerate for the same push. For a given laser power, acceleration is simply force divided by mass. Double the mass, you halve the acceleration. Multiply the mass by 5, you cut the acceleration by 5. If you want the trip time to stay under a human lifetime, say under 50 years one way, you need acceleration that's not just barely above 0. That means your laser or microwave array has to pump out truly enormous power, tens to hundreds of terawatts, focused in a tight beam, across distances measured in trillions of kilometers. On top of that, a thick, dense shield is not a great sail. A light sail works best when it's incredibly thin and lightweight, like a shiny parachute. Your armor block on the nose is the opposite of that, so you're stuck again. Keep the shield thin so the sail can be light and dust kills you. Make the shield thick enough to survive and your sail becomes so heavy it crawls instead of flies. Unless you build a power system that makes our entire planetary civilization look small. You can see the pattern now. Every fix in one area makes another area worse. That's the core of the armor paradox. To survive the sandblasting from interstellar dust and gas at high speeds, you need heavy shielding, probably meters of material. But as you add shielding, the ship's mass climbs into the millions of kilograms. Propulsion becomes harder, not easier. Structures have to be stronger and heavier to hold the shield. Radiators have to grow to dump waste heat from bigger engines. Life support has to stretch over longer trip times because you can't accelerate as fast. Then, because the trip takes longer, the total number of dust impacts and radiation dose both go up, which pushes you to add even more shielding. Try to push speed higher to shorten that travel time, and the kinetic energy of each dust grain increases with the square of speed, so impacts become deadlier. That forces you to thicken the shield again, driving mass up, which makes it harder to reach that higher speed. Survival at high speed pulls you one way, realistic propulsion, and structures pull you the other way. There's no sweet spot that looks anything like the slick steel starships in popular culture. The realistic design starts to look like a flying bunker that's almost too heavy to move. And here's the twist that makes it even worse. Dust and debris are only one threat, the one that pushes you into building the armoured bunker in the first place. Once you've done that, you still haven't dealt with another invisible killer that also demands thick shielding and extra mass: deep space radiation. The more seriously you try to protect a human crew from that radiation, the more your ship starts to look not just heavy, but completely pinned down by its own protection. Space isn't just dark and cold, it's radioactive, and the moment you leave Earth's magnetic field, you find that out the hard way. Around our planet, the magnetic field and atmosphere block and scatter most of the dangerous particles coming in from the sun and from the galaxy. On the ground, you pick up about 2 to 3 millisieverts of radiation in a whole year, from cosmic rays, rocks, and medical scans. That's your normal background. Now compare that to a deep space cruise. During the Mars Science Laboratory trip to Mars, instruments measured roughly 1 to 2 millisieverts per day in interplanetary space. Per day, not per year. In 1 year out there, you can rack up several hundred millisieverts. That's already close to, or above, what many space agencies set as a career limit for astronauts. And that's just for a Mars-class mission, a few months out, a few months back, plus some time on the surface. For interstellar travel, your baseline environment is at least that bad, and probably worse for decades. Galactic cosmic rays are constantly hitting you, high-energy protons and heavier nuclei coming in from all directions. On top of that, you still have to deal with the solar energetic particles from flares and coronal mass ejections. Space beyond Earth's shield is basically a steady, low-level, particle accelerator that your ship and your crew sit inside every hour of every day. So what happens to human bodies when you stretch that exposure? Not over months, but over entire working lifetimes, or even over generations. Radiation damage adds up. It doesn't reset because you slept well or ate a salad. If you average 1 millisievert per day in deep space, that's 365 millisieverts per year. Over 10 years, that's 3.65 sieverts. Over 40 years, that's around 14.6 sieverts. For context, a whole-body dose of about 4 to 5 sieverts received in a short time is usually fatal for humans without extreme medical care. Spread out over years, your body can tolerate more, but it pays a price. Cancer risk goes way up. The risk of cataracts, heart disease, and neurological problems rises. Tissues slowly accumulate damage they never fully repair. An interstellar mission is not a 6-month stunt. For a crewed ship going to a star 4 light-years away at realistic speeds, you are looking at decades on board, even if you somehow reach a 1/10 of light speed. For slower, more practical designs, you might be talking about missions where the people who arrive are the children or grandchildren of the ones who launched. In those timescales, hundreds or thousands of millisievers are almost guaranteed. Your Starship becomes a controlled radiation poisoning experiment, where the end state is not everyone's fine, it's everyone's damaged, some severely. So you try the obvious move. If the radiation outside is lethal over decades, then you build thicker walls and hide behind them. That sounds simple, but how bad does the mass penalty get when you actually try to do it properly? The straightforward way to shield is to surround your living areas with matter. Materials like water, polyethylene, and regolith are good because they have lots of hydrogen. Hydrogen is effective at slowing down protons and some other particles without creating as many nasty byproducts as very heavy metals. But for galactic cosmic rays, which are extremely energetic, thin shielding does almost nothing. To cut the dose by even half, you end up needing dozens of centimeters, sometimes meters of material. Picture a cylindrical habitat, maybe 10 meters in radius, about 33 feet and 20 meters long, about 66 feet. Wrap that in a 1 meter thick shell of water as a radiation shield. The volume of that water layer is roughly the volume of a cylinder of radius 11 meters minus 1 of radius 10 meters times the length. That's on the order of 1,300 cubic meters of water. At 1,000 kilograms per cubic meter, that's about 1.3 million kilograms, or 1,300 tons, just in shielding for the habitat. And 1 meter might not even be enough for serious galactic cosmic ray reduction. Now remember, in the last section, your front-end dust shield already pushed your total ship mass into the millions of kilograms. Add over 1,000 tons of water wrapped around the crew area, and you've multiplied things again. More mass means you need more propulsion to reach the same speed. More propulsion needs more power, more structure, more radiators. Every attempt to make the inside safer from radiation makes the whole vehicle heavier and harder to move. Even worse, shielding is not as simple as more is always better. At the energies we're talking about, the stuff you add to protect the crew can start doing the opposite. So what happens when those high-energy particles smash into the shielding you worked so hard to install? Galactic cosmic rays are mostly very fast protons and heavier ions like iron nuclei moving at significant fractions of light speed. When one of these hits a heavy nucleus in your shielding material, it doesn't just stop, it can shatter that nucleus and produce a whole shower of secondary particles. You get cascades of neutrons, lighter ions, and other fragments spraying further into the ship. Some of these secondaries are highly penetrating and biologically very damaging. That means there's a trade-off. Thin shielding lets a lot of primary cosmic rays through. Thick shielding stops some primaries, but it also produces secondary showers that can, in some setups, increase the dose in certain regions. There's a sweet spot thickness where you reduce the overall dose the most. Go thinner, dose goes up. Go much thicker, and parts of the spectrum get worse again. Finding that sweet spot is already complicated for a Mars mission. For a Starship with decades of exposure and many different particle energies and directions, the problem is far uglier, so you're stuck between not enough shielding, everyone gets fried slowly, and too much of the wrong shielding, you build a radiation factory into your own walls. And remember, all of this is happening on top of the dust and impact shielding we already talked about. The same mass that helps with dust might hurt with some cosmic rays, and the materials that are best for one threat are not always best for the other. Let's say, somehow, you decide to accept a higher biological risk. You tell yourself the crew will be highly selected, monitored, maybe genetically tweaked, and you'll just live with elevated cancer rates. That still doesn't get you out of trouble because the ship itself is vulnerable. What does this radiation do to the electronics that have to keep everything running for decades? Every computer on that ship, every sensor, every control system is under constant fire from these particles. High energy hits can flip bits in memory, changing a 0 to a 1 or vice versa. That's called a single event upset. Enough of those, and your software starts behaving in unpredictable ways unless you build in heavy error, correction and redundancy. More serious hits can cause latch-up, where circuits draw too much current and burn out. Over years, the total dose slowly degrades semiconductors, metals and insulators. Solar panels lose efficiency, detectors get noisy, components that worked perfectly on launch day can become flaky 20 years later. Even in Earth orbit, where the radiation environment is much milder and missions are far shorter, we already need radiation-hardened components, special shielding and constant error checking. Satellites fail early because of radiation damage all the time. Reaction wheels, control units, imaging sensors, they age and die under conditions far nicer than what a deep space starship would see. Stretch that to 50 or 100 years in deep space without Earth's magnetic field, without quick servicing missions, with occasional huge solar storms washing over your hull, and your brain is constantly eroding. Every sensor that tells you where you are, every processor that runs life support, navigation and propulsion is slowly being punched apart atom by atom. A human crew cannot survive if the digital nervous system holding the ship together fails, but the same radiation that threatens their bodies is also eating that nervous system from the inside. So now step back and look at the full picture. To keep people alive inside, you need thick radiation shielding, which adds huge mass. To keep dust from tearing you apart outside, you need thick impact shielding, which adds even more mass. The more mass you add, the harder propulsion gets and the longer the trip takes. The longer the trip takes, the more radiation dose you collect, and the more impacts you suffer. Try to cut the time by going faster, and you run into another brick wall. The very thin gas between the stars, mostly hydrogen, starts acting like a built-in particle beam slamming into your ship's nose. You're not just sitting in a radioactive background anymore, you're actively ramming into it at a significant fraction of light speed. You've added brutal armour on the front, you've wrapped the crew in thick radiation shielding, you've accepted a slow heavy ship so dust and cosmic rays are handled right, not even close. There's one more background ingredient you can't turn off: ordinary interstellar hydrogen. The same stuff that makes stars shine becomes a built-in weapon the moment you try to go really fast. Between the stars, most of the gas is hydrogen atoms, spread out at maybe 1 particle per cubic centimetre, sometimes more, sometimes less. At low speed, each atom is basically harmless. A single proton drifting into your hull at a few kilometers per second is nothing, your materials shrug it off. But when you start talking about relativistic speeds, like 30% of light speed, around 90,000 kilometers per second, about 200 million miles per hour, everything changes. Each one of those harmless atoms turns into a high-energy projectile. You've effectively turned the interstellar medium into a natural particle beam, a stream of protons slamming into your nose with energies similar to what we build in giant particle accelerators on Earth. So maybe you think, fine, each proton is still tiny, how bad can that really be when you add it up? The answer is, the total power you have to swallow is beyond anything a normal machine can handle. At around 30% of light speed, a single proton carries on the order of 10 trillionths of a joule of kinetic energy. That number is small by itself. The problem is how many protons you hit every second. Take that same 100 square meter ship nose, about half a basketball court. Flying through a region with about 1 particle per cubic centimetre at 90,000 kilometers per second, you sweep through a mind-boggling volume of space each second. That works out to something like a 3 followed by 29 zeros protons slamming into your shield every second. When you multiply that number of hits by the tiny energy per hit, you end up dumping roughly 3 billion joules of energy into your forward shield every second. That is power on the order of 10 million large nuclear power plants, all focused onto the area of a small house on the front of your Starship, all day, every day, as long as you stay at that speed. With that much energy being poured into your nose, the gas in front of you doesn't stay as cool, neutral atoms for long. It's forced into a completely different state, and that creates a new kind of problem wrapped around your ship. At those energies, your ship rams into the interstellar gas so hard that a bow shock forms. The hydrogen in front of you is violently compressed and heated into plasma, where electrons are stripped from protons. Instead of flying through a cold vacuum, you're now ploughing into a region of super hot ionized gas that you yourself are creating just by moving. This plasma piles up ahead of the nose, flows around the ship, and constantly hammers your shield. That hot plasma erodes material, sputtering atoms off the surface. It also radiates energy outward as light, including high-energy X-rays and possibly even gamma rays in the forward direction. Some of that radiation will leak deeper into the ship, adding to the already nasty radiation environment from cosmic rays. So your front shield is doing double duty. It has to stop direct kinetic hits from hydrogen and dust, and it has to survive being bathed in an artificial plasma furnace that you're dragging with you for the entire trip. So you try the next obvious trick. Hydrogen and other ions are charged, so why not push them away with a magnetic field and avoid hitting them at all? On paper that sounds like a clever shortcut, but the numbers ruin it again. To bend a fast proton away from your hull, you have to apply a sideways magnetic force for long enough that its path curves around the ship. For relatively slow particles, that's not too hard. For relativistic protons, it's brutal. To deflect them over the distances of tens or hundreds of meters, you need magnetic fields measuring in tens of Teslas, stretched over structures hundreds of meters across, forming a kind of artificial magnetosphere. For comparison, the strongest continuous magnets we run in labs are only in that ballpark inside small coils and cryogenic setups, not filling up volumes larger than skyscrapers. Now put that on a Starship. The coils or superconducting loops that create such a field would be enormous and under intense mechanical stress. The magnetic pressure on the coils themselves would try to tear them apart. They would also be sitting in the same high-energy radiation and dust environment as the rest of the nose. So the hardware you need to survive the protons is getting blasted by protons and dust. If those coils crack, quench, or lose superconductivity, your protective field collapses and your hull suddenly starts taking the full kinetic and thermal load again. And that's for charged particles. Neutral hydrogen atoms, or any dust grains that are not fully ionized yet, don't care about magnetic fields at all until after they've started interacting with your shield. Even if you somehow build these giant, ultra-strong magnetic systems powered for decades, cooled and constantly repaired, you haven't escaped the core issue. You've only shifted where the energy goes. The interstellar medium still pushes back on you with that enormous power as you move through it. Somewhere in your ship, that energy has to be absorbed and then radiated away, or your systems will heat up and fail. This leads to a quiet but very hard limit. The thin gas between the stars ends up setting a practical speed limit on how fast you can go. Below some fraction of light speed, maybe a tenth, maybe a bit more depending on local density and shielding, the energy dumped into your front end by hydrogen and dust is painful but maybe barely manageable with insane engineering. As you push toward a third, half or more of light speed, the kinetic energy of each incoming proton climbs sharply, and the number you hit per second stays enormous. The rate at which you have to absorb and throw away energy starts to rival what stars do. Your nose has to act like part of a star's surface, constantly converting incoming kinetic energy and plasma heating into outgoing radiation, without melting or breaking. Once you cross that threshold, increases in speed cost you far more in terms of heating, erosion, and radiation than you gain in shorter trip times. The interstellar medium, which looks empty on paper, becomes an effective wall. Not a clean, sharp barrier, but a curve where the engineering cost and risk explode as you get closer to light speed. Above that curve, the power you have to manage just to not vaporize your own shield makes the entire mission look less like spaceship design and more like trying to build a controlled artificial star and ride it. By this point, you're juggling dust that behaves like explosive charges, hydrogen that behaves like a particle beam, radiation that turns the inside of your ship into a long-term health hazard, and shields so heavy they crush any realistic propulsion plan. And you still haven't tackled another brutal fact. Even if you somehow build this impossible armor and push it to these insane speeds, you then have to get rid of all the excess heat those same systems create in a vacuum that's terrible at cooling anything down. You'd think one thing is finally on your side in deep space, the cold. Space is just a few degrees above absolute zero, so it should be the perfect refrigerator, right? The catch is, in a vacuum you lose the two easy ways to cool things down. You can't blow air over a radiator, and you can't dump heat into water or soil. The only way you can get rid of heat out there is by glowing, by radiating light away into the darkness. There's a simple rule from thermodynamics behind this. The power a surface can radiate depends on how big it is and on the fourth power of its temperature measured from absolute zero. That fourth power part is ruthless. Double the temperature and the radiated power per square meter goes up 16 times, not just twice. At around 300 Kelvin, roughly room temperature, a perfect black surface radiates about 460 watts per square meter. So a square meter barely handles the heat of 4 household light bulbs. Real materials are worse than perfect black, so in practice you get less than that. Space isn't a freezer, it's more like a silent, slow leak for heat. And your Starship is a machine that wants to run hot. So what happens when your ship isn't just running a few laptops and some lights, but engines and reactors throwing off serious power, continuously for years? Take a Starship trying real interstellar propulsion. You're not talking about a few kilowatts like a house, you're talking hundreds of megawatts or gigawatts. Say the waste heat you have to get rid of is around 1 gigawatt, a billion watts. That's modest for a drive that has to accelerate millions of kilograms to a good fraction of light speed, but it's already an insane number by normal standards. Now divide that billion watts by what 1 square meter can radiate at around room temperature, about 460 watts per square meter if it were perfect. You land at a required area of roughly 2 million square meters. That's 2 square kilometers of radiators, an area about 0.8 square miles, the size of a small city. All of it made from thin, lightweight panels or tubes, all of it unfolding into space, all of it needing a clear view of the cold background so it can radiate heat away. Those radiators can't point at your own hot exhaust, they can't face bright stars or your own reactor room, and they can't block each other's view. They have to be carefully oriented, like the petals of a huge metal flower, kept stable and straight for decades while the rest of the ship vibrates, thrusts, and flexes. If a few % of that area goes offline, your temperature starts to creep up. If a large chunk fails, your internal systems can't dump heat fast enough and everything starts to cook. So you might say, fine, 2 square kilometers is insane, so just run the radiators hotter. If power scales with the fourth power of temperature, turn the temperature knob up and shrink the size, problem solved. The reality is, you just trade area problems for materials and reliability problems. If you heat your radiators to around 600 Kelvin, roughly 330 degrees Celsius, about 626 degrees Fahrenheit, each square meter now radiates about 16 times more power than at room temperature. That means your required area for that same 1 gigawatt drops by a factor of 16, from about 2 million square meters down to around 125,000 square meters. That's 0.125 square kilometers, about 0.05 square miles. More like a big factory complex instead of a whole city. On paper, that looks like a huge win. But now every part of that radiator system has to sit at a few hundred degrees above the boiling point of water for years to decades, while being constantly hit by radiation and dust impacts. Many metals and composites creep at those temperatures, which means they slowly deform under their own weight or under small stresses. Welds fatigue, joints loosen, coatings peel or outgas, fluids inside the radiator loops have to stay stable, not break down chemically, not freeze, not boil off, all while being pumped day and night. Push the temperature even higher to save more area, and you run into melting points, loss of strength, and drastic chemical reactions. You can't just say, make it red hot and it will be fine, because then the structure holding the radiators together starts to sag, crack, and fail. The sweet spot where your materials survive, your pumps work, and your pipes don't explode locks in how hot those radiators can reasonably run. That, in turn, locks in how big they have to be. And all of that assumes the radiators just sit there peacefully. But remember what the front of your ship is ploughing through. Dust, micrometeoroids, and high-energy particles. What do those delicate, hot panels look like to that environment? Your radiators are thin, broad, and spread out, because that's the only way to get a lot of area without a crazy amount of mass. To a dust grain, that looks like the perfect target. Every high-speed particle that hits a radiator tube or panel punches a hole, tears a strip, or vaporizes a spot. If the radiators use liquid coolant flowing through channels, each hit risks a leak. Enough leaks and your coolant inventory drops, circulation fails, and sections of the radiator overheat. If you try to armour the radiators, you make them thicker and heavier, which both lowers their efficiency per kilogram and adds even more mass for your already overworked propulsion system. You might think, just tuck the radiators behind the main shield. But if they hide behind the big nose armour, they can't see open space, they see the back of your ship. That hot structure is glowing in infrared too, so your radiators can't dump heat effectively. They end up radiating to each other instead of to the universe. To really work, the radiators have to stick out far enough that they have their own clear view of the sky, which means they stick out into the same hostile environment as everything else. Even if you design self-healing systems with extra channels that can be opened when others fail, and robots constantly patching holes, you're fighting a losing battle. Over decades, the radiator field takes steady damage. Every loss of area forces your internal systems to run hotter, or your engines to throttle down. Now your mission profile, your schedule, and your maximum sustained power are all tied directly to how long those fragile panels can survive. So you end up with this final brutal constraint on top of all the others. Propulsion throws off heat, life support throws off heat, electronics, reactors, pumps, and even your shielding systems all generate heat. All of it has to be pushed out into space through those radiators. If you try to ramp up engine power to cut travel time, you generate more waste heat. If you thicken shields, your engines work harder, again generating more heat. You can't simply dump that extra energy into space at will. You are capped by radiator area and temperature. That means heat rejection quietly becomes the master throttle on what your Starship can do. Even if you somehow beat dust impacts with absurd armour, even if you tame interstellar hydrogen with magnetic fields, even if you keep your crew and electronics alive through radiation, you still run into a thermal budget that you can't cheat. Without enormous delicate radiators and very careful limits on power use, the inside of your ship slowly heats up until systems fail, materials soften, and habitats become unlivable. The vehicle cooks itself from within, and this builds directly into the next layer of impossibility. Because once you look at how much power you need just to get a heavy shielded ship up to a reasonable fraction of light speed, and then stop it again at the other end, you discover that the total energy bill isn't just hard, it's on the scale of entire civilizations. You're not just trying to cool a hot machine, you're trying to manage the same kind of energy that powers whole planets, and you have to do it from inside a vulnerable metal shell. Here's the next brick wall. Even before you talk about engines or fuel types, the raw energy bill for going reasonably fast between stars is already insane. Take a speed that sounds modest for interstellar travel, around 1/10 of light speed. That's about 30,000 kilometers per second, roughly 67 million miles per hour. Now take a starship with a mass of about 1,000 tons, 1 million kilograms, similar to a big ocean ship but packed into a spacecraft. When you work out the kinetic energy at that speed, you multiply the mass by the square of the speed and then take half of that. The number you get is on the order of 4.5 times 10 to the 20th joules. That's a 4 with 20 zeros behind it in joules, and that is just to speed the ship up to 0.1 c. You still have to slow it down again when you reach the target star, unless you're happy to fire the crew straight through the destination system at 1/10 of light speed. So how big is that number really, compared to something you know? Global energy use is a good reference. How much power all of human civilization uses in a year, from every power plant, every car, every plane, every data center, every home. Right now that adds up to roughly 6 times 10 to the 20th joules per year. So 1,000-ton Starship going from rest to 1/10 of light speed once costs about 3/4 of everything humanity uses in an entire year. If you want to accelerate and then decelerate, double it. You're at something like 1.5 times a full year of planetary energy use for one round of speed change for one relatively small ship. Now push the size up to something like a true ship, not a stripped down probe. Say 100,000 tons, 100 million kilograms, closer to a floating city in mass. The kinetic energy at the same 0.1 c now jumps by a factor of 100, up to roughly 4.5 times 10 to the 22nd joules. That's around 70 to 80 years of current global energy use, burned just to get that one Starship moving. Again, that doesn't count slowing down, maneuvering or any mistakes. That's best case, perfectly efficient, one-way acceleration. With numbers like that, you can see why standard rocket fuels don't just struggle, they basically fall off the table. Chemical propulsion belongs in the toy category at this scale. Take a common high-performance chemical mix like liquid hydrogen and liquid oxygen. The chemical energy per kilogram you can get out of that is around 10 million joules. To supply about 4.5 times 10 to the 20th joules, you divide by 10 million, and you end up needing on the order of 10 trillion kilograms of fuel, just for the kinetic energy, ignoring engine inefficiencies. 10 trillion kilograms is 10 to the 13 kilograms, more mass than many large asteroids. You're not filling some big tanks, you're talking about mining entire small worlds just to build the propellant stockpile. Even if you bump up to fusion, which can in theory give you around 10 to the 14 joules per kilogram of fuel, the story is still ugly. You would need millions of kilograms of fusion fuel handled safely, confined, ignited in a controlled way, and processed with engine efficiencies that are far better than anything we have today. And again, that's only to get up to speed once, not to turn around, not to stop, not to dodge anything. So the next move is to say, fine, don't carry all that fuel, move the energy source off the ship and push it from afar. Light sails and beamed power look like the clever answer here, but they only shift where the impossible part sits, they don't make it go away. With a light sail, you spread a huge, thin, reflective surface and you shine powerful lasers or microwaves at it from the home system. The pressure from the photon slowly accelerates the sail and the payload. The ship itself doesn't need propellant tanks, which neatly avoids the rocket equation on board. But now you need a power source back home that can produce gigawatts to terawatts of coherent beam power, non-stop for years. A terawatt is 1 trillion watts, about the average electricity consumption of the entire world. To push a heavy, shielded Starship to 1/10 of light speed in a human lifetime, you probably need many terawatts. You're dedicating a big fraction of your planet's entire energy economy, or several planets' worth, to push one vehicle. Then there's the beam director. You need optics, mirrors, or phased arrays that are kilometers across, bigger than cities, perfectly aligned and phased so that the beam stays tight across distances of billions to trillions of kilometers. Any tiny pointing error, phase jitter, atmospheric disturbance if you're firing through air, or structural vibration in your array, shreds the beam and weakens the push. On top of that, the beam itself is dangerous. A misaligned multi-terawatt laser is not a harmless pointer, it's a weapon that could torch anything unfortunate enough to sit in its path. Even if you solve all that, Every joule you pour into the ship's kinetic energy is still real, and it all has to be accounted for. None of it is abstract. If you spend around 10 to the 20th to 10 to the 22nd joules getting a starship up to speed, that energy doesn't disappear. It's stored as the ship's motion. When you want to slow down, you have to remove that energy somehow, usually by firing a drive in reverse or by interacting with some external medium. If your deceleration burn is late, wrong, or fails, you don't just overshoot the target system, you hit it at 1/10 of light speed or more, carrying that kinetic energy straight in. For scale, the asteroid that helped end the dinosaurs released on the order of 10 to the 23 joules when it hit Earth. A 100,000-ton starship at a few tenths of light speed has kinetic energy in that same ballpark, maybe a fraction of it, maybe more depending on mass and speed. That means, purely by having one of these ships in your civilization, you're holding something that is by definition a potential extinction-level weapon. Even routine maneuvers, like shedding speed using a beam or dumping exhaust at relativistic speeds, involve power levels and energy flows that are hard to handle safely. The exhaust plume from a fusion drive at these scales is not just hot gas. It's a directed blast of energy that could fry anything in its way. Every joule you use to accelerate has to end up as a something: ship motion, exhaust heating, radiation, weapon scale beams, or shock heating in a target system if things go wrong. And once you accept that the energy scale for interstellar travel is measured in multiple years of total planetary output, you bump into a final harsh conclusion. Any realistic interstellar ship has to be tied to a civilization capable of handling, directing, and controlling those vast energies. But the very same physics that lets you launch the ship also makes that ship, and even its support infrastructure, almost unimaginably dangerous. And here's where the next nightmare kicks in. So far, we've mostly talked about energy itself, how much you need, and to what it can do. But if your propulsion system is a rocket that carries even part of its propellant, the situation becomes worse than just need a lot of fuel. The rocket equation steps in and tells you that as soon as you ask for these huge changes in speed, and you insist on hauling your fuel with you, your starting mass explodes exponentially. The same ship that was already heavy from shielding and structure now disappears under a mountain of propellant, and most of your mega-engineered vehicle is nothing but fuel you throw away. You've seen how the raw energy bill for interstellar travel is brutal. Now add the rule that decides how much fuel you actually have to carry if you want that energy to come from a rocket. This is where the rocket equation quietly destroys almost every classic Starship design you've ever seen. The basic idea is simple. The change in speed your rocket can achieve depends on three things: how fast your exhaust leaves the engine, how strong gravity is, and the ratio between your starting mass and your final mass after burning fuel. That last part, the mass ratio, is the killer. The relationship involves a natural logarithm, which means as you ask for more and more total change in speed, the required mass ratio doesn't grow gently, it explodes. To double your total speed change, you don't just double the fuel, you often multiply it by many times. So what does that mean in practice? It means that if you want a big total change in speed, your starting mass, fuel plus ship, has to be much larger than your final mass, the ship and any leftover hardware. That ratio, starting mass divided by final mass, shoots up into ridiculous territory as soon as you demand interstellar level speeds. And remember, for a starship you don't just need to speed up once, you have to slow down at the destination and maybe maneuver and maybe even come back. Every extra piece of delta V you add to the mission profile stacks on top of this exponential behavior. You don't have to take this on faith. You can look at a real rocket we actually built and see how quickly the pain sets in, even for tiny speeds compared to light. The Saturn V rocket, which sent humans to the moon, is a good example. On the launch pad it weighed about 3,000 tons. The mass that finally ended up leaving Earth for the moon was only a small fraction of that. The overall mass ratio from liftoff to final spacecraft was on the order of 20 to 1. And what did that buy you? A total speed change of around 11 kilometers per second, about 7 miles per second, just enough to get off Earth and head toward the moon. Now look at what you're asking of an interstellar ship. To cruise at a tenth of light speed, you're talking about around 30,000 kilometers per second of speed, roughly 18,600 miles per second. That's almost 3,000 times higher than 11 kilometers per second. Even if you grant yourself a miracle engine with exhaust velocity 10 times better than what Saturn V had effectively, you'd still be hundreds of times short in terms of what you can reach with a reasonable mass ratio. The math pushes you into starting mass to final mass ratios so enormous that your rocket is almost pure fuel with a tiny token spacecraft on the front. So the obvious next thought is, fine, chemical rockets are hopeless, but nuclear stuff is way better, right? Sadly, the rocket equation doesn't let nuclear ideas off the hook either. It just moves the problem around. Nuclear thermal rockets, which heat hydrogen using a nuclear reactor, can roughly double the specific impulse compared to the best chemical engines. Instead of exhaust streaming out at maybe 4 kilometers per second, you might get something like 8 or 9 kilometers per second. That's great for missions inside a solar system. It cuts fuel needs and makes Mars trips more practical. But when your target speed is a significant fraction of light, tens of thousands of kilometers per second, a factor of 2 improvement is nothing. The exponential curve barely moves. Fusion rockets look better on paper. Fusion reactions pack about 1,000,000 times more energy per kilogram than chemical reactions. That could, in theory, give you exhaust velocities of thousands of kilometers per second or more. Matter-antimatter annihilation goes even further. Now, your exhaust could reach tens of thousands of kilometers per second, but as you crank exhaust velocity up, your engine stops being a compact box and starts looking like a full-scale power plant. You need heavy magnetic fields, massive radiators, complex fuel storage, shielding against your own radiation, and huge safety margins. The engine stops being free mass. It becomes a big chunk of your final mass. And even with that, the rocket equation still insists on enormous fuel fractions if you carry your own propellant. You might move from a mass ratio of, say, 1,000 to 1 down to 100 to 1 for a given mission. But 100 to 1 still means 99% of your starting mass is fuel and tanks you throw away, and only about 1% is the actual Starship you care about. That's the win you get after inventing perfect fusion drives. It's better, but it's not suddenly easy. So you could say, okay, we'll do what Saturn V did and just use multiple stages. Throw away each empty chunk as we burn it and keep the top part light. That's how we reach orbit. Can staging rescue interstellar plans? Staging absolutely helps. Each stage starts with its own fresh mass ratio, and when it's empty, you drop it, so the next stage doesn't have to drag that dead mass. That's why reaching orbit is possible at all with chemical rockets. But for interstellar speeds, the numbers of stages you'd need become absurd. If each stage can only reasonably give you a modest fraction of the total delta you need, you have to stack them like a totem pole. Imagine a starship where the final crude module is the size of a large space station. Now imagine that attached to the back of it are 10, 20, maybe more stages, each one the mass of a Saturn V or bigger. All built in orbit, all fueled, all just waiting to be burned and tossed aside one after another to push that final little payload up to 1/10 of light speed and then do the same again in reverse to slow it down. You're basically constructing and throwing away a small civilization's worth of hardware, just to send one group of people and some cargo to a single nearby star. The engineering effort to build that many huge stages, assemble them, test them, and accept losing them forever in one mission is beyond anything we've ever attempted. And remember, all of those stages need to be armoured, shielded, and cooled against dust, radiation, and waste heat too, because they're part of the same insane environment. Staging makes the math slightly less brutal, but it doesn't make it sane. When you add all this together, the message from the rocket equation is blunt. If you want true interstellar class total speed change, and you insist on carrying all your propellant from the start, you're in deep trouble. The mass ratios blow up, the number of stages explodes, and the share of your starting mass that is actual ship shrinks towards zero. That's why, in serious discussions, people keep ending up at the same conclusion. For truly high-speed interstellar flight, you probably cannot bring all your fuel with you. You're pushed toward ideas where the energy comes from outside, or where you refuel along the way, or where you barely accelerate at all and just drift on very long timescales. External power means light sails and beams, with all the problems we already talked about. Giant arrays, insane power, terrifying weapon potential. In situ refueling means counting on usable reaction mass scattered through interstellar space or guaranteed fuel sources in every star system you visit, something we have zero evidence for at the precision you'd need. Riding stellar winds or magnetic fields means trusting interactions we can barely test in small probes today, and hoping they scale up to million-ton starships without surprises. And all of these solutions leave the other problems intact. The dust is still there, the hydrogen is still there, the radiation, the heating, the structural stress, and the maintenance nightmare are still there. The rocket equation simply adds one more layer. If your plan involves rockets and carried fuel, the mass you need explodes before you ever leave home. But even if you somehow magic the propulsion piece away with perfect external beams or exotic physics, you're still trying to push a huge, flexible, fragile structure, kilometers long, through a violent environment for decades. That structure twists, vibrates, heats and cools. Every thrust, every dust hit, every temperature cycle is trying to shake it apart. The next problem isn't just how to move the ship, it's how to keep the ship from tearing itself to pieces while it moves. By now your starship is heavy, shielded, and powered by something close to magic just to get moving. But there's a quieter problem that doesn't care what your engine is. The ship itself doesn't want to stay in one piece. A practical interstellar craft has to be huge, and huge, light, and stiff is a contradiction that engineers already struggle with on Earth. You need a big vehicle because you need thick shielding up front, deep radiation shelters, massive radiators, long propellant tanks or sail structures, and probably large habitats if humans are on board. That easily pushes the total length into hundreds of meters, maybe kilometers. Long structures have natural vibration modes, like musical notes on a guitar string, but in steel and composite instead of wood. Even small forces, like changes in thrust, tiny misalignments in engines, or uneven heating along the hull can excite those modes. On Earth, bridge designers spend years trying to stop kilometre-long bridges from wobbling in the wind. Your starship is basically a flexible bridge in space, with engines strapped to one end and random hits from dust along the way. When the engines fire, any asymmetry in thrust tries to bend the ship. When you turn, inertia wants to keep the long, massive front section going straight. That bending energy travels as waves up and down the structure. If the timing of thrust pulses or control movements matches one of the ship's natural frequencies, those oscillations grow. You get shaking, then more shaking, then real stress in joints and connections. You can add bracing and dampers, but every extra truss, every thicker beam adds more mass, which the engines have to push, and which changes the vibration behaviour again. It's a feedback loop that's very hard to tame over kilometre scales. Then you add another requirement. You don't want your crew floating in microgravity for decades, because that slowly wrecks their bodies. So you try to fake gravity by spinning part of the ship. That gives you another huge structural load, always on, never turning off. Take a rotating habitat ring with a radius of about 100 meters, a little over 300 feet. Spin it fast enough that people on the outer edge feel 1g, about 9.8 meters per second squared. That works out to a rotation period of roughly 20 seconds per full turn. Inside, the crew feels a stable floor under their feet. From the structure's point of view though, the ring is being pulled outward all the time. The spokes or supports connecting the ring back to the central spine have to hold up the equivalent of thousands of tons of weight, continuously for years. Now add the real environment. While the ring spins, dust impacts are randomly punching it. Heating is changing as parts move in and out of any external lighting, and the whole assembly may be under occasional thrust. Every impact that hits the ring or a spoke while it rotates creates a brief extra load in one direction. Over time, that repeated stress can lengthen bolts, stretch cables, and open micro cracks. You cannot simply stop spinning whenever you want, because then the crew loses their 1G environment and their health starts to slide again. The rotating section adds a constant, unrelenting structural demand on top of everything else. Thermal stress is another slow killer. Even without an atmosphere, your ship doesn't stay at one uniform temperature. Parts that face stars or engine plumes heat up, shadowed parts cool down, and internal systems turn on and off. If you don't manage it carefully, different parts of the hull and truss can see swings of hundreds of degrees Celsius, hundreds of degrees Fahrenheit, between hot and cold zones. Materials expand when they get hotter and contract when they cool. Joints, welds, bolts, and composite interfaces all feel that movement. On the International Space Station, which orbits Earth every 90 minutes, components get cycled in temperature and stress daily, and that's in a relatively mild environment with active thermal control and constant maintenance. Stretch that out to a starship with bigger structures and longer, harsher cycles over decades, and you have a recipe for thermal fatigue. Tiny cracks start at stress points. Each cycle opens them a bit more. Eventually those cracks link up into real fractures. A bracket fails. A panel loses its support. A truss member no longer carries the load it was designed for. Then remember, this ship is not flying in quiet air. Every dust hit at 0.1 C is not just a small hole, it is a sharp mechanical kick delivered at a specific point on the structure. Each hypervelocity impact sends a shock into the local material. That shock spreads as a quick, intense pulse through beams, plates, and joints. Some of that energy dies out as heat. Some of it reflects back and forth, but some lines up with the ship's natural bending and twisting modes. Over years, tens of thousands, maybe millions of such hits feed random impulses into the structure. Some days it's quiet, other days a cluster of hits lands while the engines are firing and the ship is turning, and you get coupled vibrations that stress certain sections much harder than the design average. You're asked to design a frame that is light enough to accelerate, stiff enough to hold alignment for optics and engines, and tough enough to take this constant mechanical abuse without losing integrity. If you overbuild it, you blow your mass budget and can't reach the required speeds. If you underbuild it, it warps, resonates, or tears over time. Finding that balance is not just difficult, it may be impossible for a system that has to survive for half a century or more without outside help, and that's the last cruel part. On Earth, when big structures age, we fix them. You close a bridge lane for repairs. You pull an airliner into a hangar and strip it down. You dry dock a ship, sandblast rust, and weld in new plates. For a starship between stars, none of that is available. Once you commit to an interstellar mission, the main structure of your craft is on its own. There are no orbital shipyards along the way, no spare kilometre-long spine sitting in storage. You can send crews in suits or robots to patch cracks, add braces, and swap out local components. But the core backbone, the giant trusses that hold the nose shield, the reactors, the radiators, the spin habitat, all in precise alignment, those were built once, at home. Over tens of years, small issues stack up. A slightly bent member here, a partially fractured joint there, a region with more micro cracks than expected. All of that hidden damage quietly reduces your safety margin. One day, decades in, you fire a maneuver that would have been routine on day one. A small course correction, a rotation of the ship, a spin up or spin down of the habitat ring. This time the weakened frame can't handle the load. A truss fails, load shifts suddenly, more members snap in a chain reaction. The ship doesn't die from a single dramatic impact, it dies from the sum of a million minor stresses that no one could fully track. So you now have a vehicle that is too big to be stiff, too long to be easy to control, too stressed to be trusted forever, and completely beyond any dry dock or rebuild. And yet you still haven't talked about another slow, relentless effect that eats at everything on board, even when the structure holds together. Materials age, lubricants dry out, electronics drift. Time and corrosion don't stop just because you're in a vacuum, and over a century-scale mission, They attack every seal, wire, chip and bearing you counted on. Space doesn't stop your ship from aging. It just changes how it ages and stretches the timeline until problems you usually ignore become mission killers. Look at what we actually fly today. Voyager 1 and 2 have lasted more than 45 years, which is impressive, but they're already dealing with failing instruments, memory issues, power loss, weird telemetry. Hubble needed multiple servicing missions in just a few decades to swap gyros, computers and hardware. The James Webb Space Telescope is designed for maybe 10 to 20 years of operation. None of these machines were expected to run flawlessly for a century or more because the people who built them know the truth. Materials, lubricants and electronics eventually break down, even in vacuum, even in deep space. An interstellar starship is asking for far more. You're not asking for 10 good years, you're asking for 50, 100, maybe longer. You can't retire it, you can't dock it, you can't send a shuttle with spare parts every few years. You need it to stay healthy for longer than any machine we've ever built has been tested. That's not just a scale-up, that's a completely different problem. Take polymers and adhesives, the glues, sealants, coatings and cable jackets that hold modern systems together. In vacuum, these don't just sit there. Molecules slowly evaporate away, a process called outgassing. Flexible materials become brittle. Adhesives lose strength. Insulation on wiring can crack. Metals under constant load don't stay perfectly rigid either. They creep, meaning they deform very slightly under stress at the microscopic level. Over a few years, that's tiny. Over a few decades, that creep can change how loads are distributed in a joint or how a seal presses on a mating surface. You probably don't see it in year 3, you barely see it in year 10, but by year 50 a gasket that once sealed a coolant line may have shrunk and hardened enough to start leaking. A cable harness that was snug in its clamps may start to sag and rub. A structural joint may no longer share loads the way it was meant to. All of these minor shifts stack up, and sooner or later one of them lines up with a dust impact, a thermal cycle, or a thrust event, and the result is a real failure. You might assume that corrosion needs oxygen and water, so in vacuum you're safe. You're not. You've just swapped one set of chemical problems for another. High energy radiation and particles passing through materials knock atoms out of place and break chemical bonds. That creates reactive fragments, radicals, and defects inside solids. Over time, plastics discolor and weaken from radiation alone. Glass can darken. Electronic components, which rely on very precise arrangements of atoms and crystals and thin films, suffer displacement damage. Atoms in a semiconductor lattice get kicked into the wrong spots. Tiny charge traps build up in insulating layers. At first, you get more noise in sensors or slightly shifted voltages in circuits. Then error rates climb. Devices that met their specs on launch day start failing to switch cleanly or leaking current where they shouldn't. Eventually, whole boards or chips just die. All of this can happen even in passive components that aren't powered at the time. The space environment is constantly editing your hardware at the atomic scale, whether you're using it or not. Now, add the parts of the ship that move. Bearings, pumps, fans, valves, reaction wheels, gimbals, all the mechanical systems that steer, cool, and stabilize the ship. On Earth, these parts are serviced, lubricated, and replaced regularly. In space, they rely on carefully chosen lubricants or ultra-smooth surfaces. Lubricants can evaporate in vacuum, especially light components. They can also break down under radiation, changing viscosity, or forming gunk and deposits. Reaction wheels on real satellites often fail within 10 to 20 years, even in relatively benign Earth orbit. Pumps seize, valves stick. On an interstellar mission lasting several human lifetimes, every moving part has to either be close to immortal or be replaced along the way. Near-immortal mechanisms are not something we know how to build at scale. You can over-engineer some components, oversize bearings, run them at low speeds, use solid lubricants, but for thousands or millions of parts you will still see wear, So you're pushed toward the other option, planning to replace almost everything important as it ages. That, in turn, means you need storage for huge numbers of spare parts, or the ability to manufacture replacements on board or both. Once you're talking about building new pumps, valves, circuit boards, and structural sections mid-flight, you're not running a ship anymore. You're running a small industrial ecosystem. Even if you do all this, probability is still against you, because big systems fail not just from single parts, but from interactions between many parts. Think about the scale. A Cirrus Starship easily has millions of components that matter, from major reactors and computers down to tiny sensors and control chips. Suppose very generously that each critical component has a 99.9% chance of surviving a 50-year mission. That is already wildly optimistic for many parts, but let's give it to you. The chance that all of those million components make it through the whole mission is that 0.999 raised to the millionth power. That works out to a survival chance of only around 37%. In other words, even with extremely optimistic per-part reliability, there's a roughly 2/3 chance that at least one critical component fails over 50 years, and that's just one pass at the math. In reality, many parts will have lower survival chances. Some components depend on others, some failures cascade, some cannot be repaired with the tools and materials you have on board. As you stretch mission length from 10 years to 50, then to 100, the odds that something you absolutely needed dies approach 100%. You can fight that with redundancy, triple backups, fault-tolerant software, self-healing networks, and constant repair work, but you never get rid of the fundamental trend. Time itself is an enemy you can slow down, but not defeat. So far, all of this has been about the ship as a machine, metals, plastics, circuits, pumps. The blunt truth is, even that machine is barely able to survive a full interstellar trip on paper, and that's assuming heroic engineering everywhere. Now layer on top of that the most fragile, least radiation tolerant, least vacuum compatible hardware you have: human bodies and human minds. You're not just asking a vehicle to last for decades under constant stress. You're asking biological systems that evolved in 1G, thick atmosphere and narrow temperature and radiation ranges to function inside that vehicle the whole time. Microgravity, radiation, closed ecosystems, and isolation each hit humans hard on their own. Put them together for decades in a ship that is slowly wearing out, and the survival problem jumps from probably impossible mechanically to almost certainly impossible biologically. How do you keep a human body working for decades in a place it was never built to live? That's the core problem. You're not just flying metal through space, you're flying soft, water-filled computers that only function properly in 1G, behind a thick atmosphere, bathed in Earth-level radiation. Take that system away from its home environment, and it starts to fail fast. Start with gravity. In microgravity, your body reads no load, has no need to maintain muscle and bone. On the International Space Station, astronauts lose around 1 to 2% of their bone mass per month if they don't follow strict exercise routines. Muscles in the legs and back weaken. The heart doesn't have to pump blood uphill, so it deconditions. Fluids shift toward the head, faces puff up, pressure inside the skull changes, and eyesight can get worse. Even with hours of daily exercise, careful diet, and constant medical oversight, a 1-year mission leaves measurable, sometimes permanent changes. Now stretch that to an interstellar flight. Even if you use a spin ring to give something close to 1G most of the time, there will be periods of microgravity, construction phases, emergencies, repairs, maneuvers. Some designs might aim for Mars-like gravity, around 0.38 G, to save structural mass. We don't actually know if partial gravity is enough to stop bone loss, muscle atrophy, and the other problems. You'd be running a decades-long medical trial on your entire crew, with no way to bring them home if the answer turns out to be no, it's not enough. A ship that fails structurally kills you quickly. A gravity environment that's even slightly off may just destroy you slowly. Then layer radiation on top of that. You're not just dealing with one short intense blast, you're dealing with a constant low-level dose that never goes away. Earlier we talked about deep space radiation levels. Hundreds of millisieverts per year, easily climbing into the thousands over a long mission. Long-term cancer risk roughly tracks total dose. Hundreds to thousands of millisieverts mean a big fraction of your crew will likely face serious cancers at some point in their lives. But it's not only cancer. Chronic radiation exposure also damages blood vessels, raises the risk of heart disease, and can affect the brain. Cells in the nervous system don't divide much, so when they're damaged, they don't get replaced easily. You're asking organs that evolved with the Earth's thick air and magnetic shield overhead to tolerate a slow drizzle of ionizing damage for decades, inside a ship that itself is already being eaten by the same radiation. Suppose you're bold and decide to accept that biological hit. You say, we'll pick the healthiest, we'll monitor like crazy, we'll treat problems as they come. That still leaves a massive systems challenge, keeping their environment livable. Closed ecosystems are far harder to run than they look in concept art. On paper, a closed loop is simple. Plants take in carbon dioxide, give back oxygen, humans breathe oxygen and eat the plants, microbes break down waste, nutrients cycle around. In practice, even a carefully built system on Earth, like Biosphere 2 in Arizona, struggled to keep oxygen and food levels stable for just 2 years. Oxygen dropped, carbon dioxide spiked, soils behaved in unexpected ways, and people lost a lot of weight. And that was with outside help, constant monitoring, and the ability to bring in supplies or change procedures whenever they needed. On a Starship, the life support loop can't fail for even a few weeks without serious consequences. You have to control oxygen, carbon dioxide, humidity, trace gases, microbes, plant growth in insect populations if you use them, and food output all at once over tens of years. A small drift in nutrients could crash a crop. A microbe you didn't plan for could bloom out of control and foul water systems. A filter that clogs a bit earlier than expected could cause toxic gas buildup. There is no outside resupply, no quick swap out of an entire habitat. The ecosystem is the ship, and if it slides outside its narrow safe band, people get sick or starve, and humans are not just chemical systems. They're social primates packed with emotions and expectations that evolved in tribes, on open landscapes under a sky with weather and changing seasons. You're putting them in a metal can and telling them, you and your descendants will live here for the rest of your lives. We already see what isolation and confinement do in submarines, Antarctic stations and space stations. Crews get irritable, depressed, anxious. Conflicts grow. Those missions last months to maybe a year, and people know they're going home. A generation ship or even a decades-long mission flips that. People are born on board, grow up inside a corridor, and die without ever seeing a sky. The group that arrives at the target star is not the group that left. They may not share the same goals, values, or willingness to follow the original mission plan. No simulator can fully predict what long-term culture drift, power struggles, and mental health issues will look like in that setting. You can write rules, you can form councils, you can pump in entertainment and education, but you're still betting your entire mission on the stability of a small human society under constant pressure, with no exit. At this point, a lot of people throw up their hands and say, fine, don't send humans, send robots, or upload minds into computers and send those. That sounds like a clean escape, but it just replaces one set of impossible demands with another. Our best robotic systems today are incredibly capable in narrow tasks, but brittle outside of them. Mars rovers move meters per day, not thousands of kilometers per second. Autonomous repair robots that can diagnose and fix damage across an entire starship under random failure modes don't exist. Even if you had super advanced AI, it still needs hardware, sensors, actuators, memory chips, power supplies. All of that hardware is vulnerable to the same radiation, aging, and mechanical stress we talked about earlier. Uploading minds, if it's even possible, wouldn't erase the hardware problem either. Those uploads would run on physical processors, in physical memory, inside physical housings. You'd still be shipping soft, complex patterns, just now encoded in silicon instead of neurons, and those patterns would still be sitting in an environment optimized to erase complexity, high radiation, constant impacts, thermal stress, and no external help. Biological brains are unmatched in adaptability and fault tolerance, but they are the least suited hardware for high radiation interstellar vacuum. Digital minds are easier to copy, but the machines they run on are even more directly sensitive to radiation and aging, so you're trapped. Humans are adaptable but fragile. Machines can be tougher in specific ways but are brittle in others. Both require stable environments, continuous maintenance, and protection from the same hostile galaxy. And you're trying to provide that protection with a starship that itself is shaking, eroding, heating, and wearing out. All of that pushes you toward one more brutal conclusion. If the ship cannot rely on help from outside, and if the crew and machines are guaranteed to age and fail, then the only way it survives is by becoming its own support civilization, with factories, workshops, farms, labs, and highly autonomous systems. At that point, you're not designing a vehicle, you're designing a small, isolated, planet-level infrastructure and hoping it can maintain itself with no backup for a century. Look at how much babysitting our current spacecraft need just to stay alive a few hundred kilometers above Earth, then scale that to light years and you see the real problem. Your Starship cannot call for help. The International Space Station flies only about 400 kilometers, roughly 250 miles over your head with regular cargo ships, constant control from the ground, and a crew of several doing maintenance almost every day. Even then it needs multiple spacewalks per year. New batteries, new solar arrays, new pumps, new computers. If something truly critical failed and couldn't be fixed, the crew could climb into a return capsule and be back on the ground in a few hours. On an interstellar ship, there is no resupply, no spare rocket coming up with new parts, no emergency return. If a key system stops and you can't recover it, abort just means die where you are. There's no safe harbour, no nearby station, and no quick exit. So everything that keeps you alive and moving has to be repairable, by you, with what you brought and what you can build on board. You can try to fight that by loading the ship with spares, racks of pumps, pallets of valves, bins of circuit boards, extra gyros, backup radiators. For some failures this works. A pump burns out, you unbolt it and swap in a new one. Control board fries, you replace it from storage. That's what we do now with satellites and stations, except the human hands and spare parts are down here, not up there. But complex systems rarely fail only in ways you predicted. They break in ways you didn't model. A coolant leak doesn't just burn out a pump, it corrodes a custom manifold you only machined once. A microscopic crack in a unique reactor housing grows slowly for 30 years, then suddenly lets coolant into a place it should never be. A sensor glitch in a guidance chip couples with a software bug and sends a slow, unnoticed drift into your navigation system. There is no spare for one-off welded assembly that only existed in the shipyard, unless you can build that assembly again from raw stock. On Earth, when that happens, you call the manufacturer, you pull old drawings, you bring the thing into a shop, you fabricate a fix, you test it, and then you ship a replacement. On the way to Proxima Centauri, there is no manufacturer, no shop outside your hull, no friendly engineer on the other side of a phone. If the part you need is not on board, your only option is to make it yourself. That leads directly to a brutal fork. Either you accept that certain failures will kill the mission, or you try to make the ship almost fully self-sufficient. To be truly self-maintaining over centuries, the ship's repair capability can't just be a couple of 3D printers and a machine shop. It has to be a full manufacturing stack. You need raw materials, which means mining or harvesting from somewhere, asteroids or your own structural mass. You need refining to separate metals, gases, and other elements. You need smelting and alloying to get the exact steel, titanium, aluminum, or exotic materials your designs require. You need precision machining for pumps and valves, high-precision optics for sensors, vacuum systems and clean rooms for electronics, full chip fabrication to make new processors and memory, bioreactors and farms to grow organics, plastics, and pharmaceuticals. That's not a workshop, that's a small planet's industrial base, shrunk and squeezed into a hull that is already overloaded with shields, reactors, and habitats. Every layer of that industrial stack costs mass, volume, power, staffing, and complexity. You need people or machines trained to run it, spare tools for the tools, maintenance plans for the factories that are supposed to do maintenance. The more you add, the more things there are that can break, and the more energy you need to keep the whole thing running. You're trying to embed an entire civilization's repairability into a single isolated object and expect it to last longer than most human institutions do on an actual planet. Some people try to jump over that by saying, we'll just let AI handle it. Super advanced AI runs the ship, diagnoses every fault, designs new parts on the fly, runs the printers and factories, and keeps everything humming. It sounds neat, but it doesn't remove the physical limits. It just pushes them onto a different layer. Any AI, no matter how clever, still needs hardware. It needs processors, memory, storage, communication lines, cameras, spectrometers, manipulators. All of that hardware ages under radiation and thermal stress exactly like everything else. Sensors degrade, actuators wear out, memory cells get a bit flipped and fail. The AI cannot fix its own brain if the physical substrate that brain runs on is damaged beyond repair. And it can't think a cracked power bus or a burned out motor back into working order without tools, materials, and time. There's also the risk side. If you rely on one central ultra-capable AI to run critical repair operations, a single mistake in one of its procedures can destroy infrastructure you cannot replace. Misjudge tolerances on a reactor part, run a coolant loop too hot, miscalculate a stress test on a structural brace, and you could wreck the only copy of a core system. On Earth, you'd build another reactor or bring in outside help. In deep space, there is no second copy waiting in storage. One bad call is final. You can try to spread the intelligence around, put many smaller AIS or automated systems in charge of their own subsystems, but then you have coordination problems, conflicting decisions, and even more components that can fail. Intelligence, human or artificial, doesn't magically freeze entropy. It can only react to it, and only as fast and as accurately as the hardware and sensors allow. That is where the deepest limit shows up. Over long enough timescales, every complex system decays. Without a huge external pool of resources, redundancy, and new parts, exactly what a full planet with billions of people and industries provides, the ability to repair and replace slowly declines. You cannibalize less critical systems to keep critical ones alive. You downgrade performance to stretch life. You accept more and more temporary patches that never get a full fix. The further you get from home, the more cycles of repair on repairs you've gone through, the more your ship drifts away from its original design state. Documentation gets out of date, replacements aren't quite to spec, workarounds pile up in software and hardware. At some point decades in, the idea that the ship is still operating as designed stops being true. It's just operating in whatever degraded state it has managed to reach, held together by improvisation and luck. In that regime, the phrase reliable operation loses meaning. You're not running a certified system anymore. You're running a one-off artifact of history, with unknown weak points, hidden damage, and parts nobody on board fully understands. Every maneuver, every repair, every mode switch carries unknown risk. That's what entropy looks like on the scale of a century-long mission with no support. And even if you could somehow keep this patchwork machine moving and powered, you'd still have to point it with extreme precision through a galaxy full of moving targets and invisible bullets. Your sensors are aging, your computers are glitching, your structure is flexing, and you're trying to hit a star system that will not be where you aimed when you left. The next problem is not just keeping the ship alive, it's steering that dying, drifting giant through a shifting minefield without hitting anything that ends the story in a single microsecond. You can build the toughest ship you can dream of, but if you can't point it and thread it through the galaxy with absurd precision, you still lose. The stars you're aiming at are not fixed pins in a black dome, they're moving targets, and you're firing a giant, fragile projectile at them from light years away. Take Proxima Centauri, about 4.24 light years away. On a star chart it looks frozen, but in reality it's moving through the galaxy at tens of kilometers per second, tens of thousands of meters every second, just like the sun. Over the decades your ship is in flight, that motion adds up to billions of kilometers of drift. If you point your ship at where Proxima is now and just go straight, you miss by a huge distance when you finally cross its neighborhood. So you have to predict that motion in advance, calculate where the star and its planets will be decades from now, and point at that future position. Then you have to correct as you go, because your initial measurement of its motion is never perfect. And gravity from other stars, gas clouds, and the galaxy itself all nudge everyone's path slightly. All of this must be done by engines, sensors, and computers that are aging under radiation, being shaken by a thrust, and being hit by dust. It's not aiming a rifle at a target on a range, it's aiming a slowly bending spear at another moving spear, in the dark with your hands going numb over time. How accurate do you have to be for that to work? The answer is far beyond what most current spacecraft can manage, especially while under continuous stress. If your goal is to arrive within about 1 astronomical unit of your target star, about 150 million kilometers, 93 million miles, that's already a big hitbox by human standards. But seen from 4 light years away, that 1 astronomical unit circle is tiny. The angular error that corresponds to a 1 astronomical unit miss at 4 light years is roughly hundredths of an arc-second. To be comfortably inside that corridor, and then aim for planets or specific orbits, you really want to do much better down into millionths of an arc-second, micro-arc-second level pointing. That's the kind of resolution used in the best astronomical measurements, not in rocket guidance under thrust. Now imagine maintaining that precision while your ship is firing engines, flexing under load, shedding heat through huge radiators, and taking random kicks from dust hits. Every slight misalignment in your thrust vector, every small bias in a sensor pointing angle, turns into millions of kilometers of error by the time you reach the destination. You can correct mid-course, but every correction costs fuel and time, and your navigation instruments themselves are slowly degrading. So you might say, fine, we'll just correct often and nudge the course as needed. But those nudges are not free, and the galaxy is not a smooth, uniform medium you can pre-map once and forget. Every course correction eats into your delta V budget. You design the mission with a certain amount of propellant or beamed momentum to accelerate, a certain amount to decelerate, and a small reserve for steering, but you cannot know every dust cloud, gas clump, or stray rock between here and there in detail before you launch. If your forward sensors pick up a denser patch of interstellar medium or a region with more dust and rocks than expected, you face a bad choice. Either you fly through it, risking higher impact rates and possible lethal hits, or you burn extra fuel to bend around it. Do that once, maybe you're fine. Do it 10 times because the galaxy is messier than your models and your safety margin shrinks. You might end up with not enough delta V left to slow down properly at the destination, or not enough to dodge a truly dangerous object you only see late. Navigation stops being a clean geometric problem and turns into resource triage. Which risks do you accept, and how much future safety do you spend to avoid the ones right in front of you? All of this assumes you can see trouble coming in the first place. But at high fractions of light speed, the universe doesn't look the way it does from your backyard. As your speed climbs, aberration of light squeezes the visible sky into a forward cone. Stars that would normally be to your side get visually pushed toward the direction of travel. Radiation from dust and gas in front of you gets blue shifted, sliding to higher energies, into ultraviolet X-rays, even gamma rays at very high speeds. On top of that, at interstellar speeds, you generate your own bow shock and plasma sheath in front of the ship, a glowing, hot region of disturbed gas and fields. Your forward sensors now have to look through that mess. Instead of a clean dark backdrop with crisp stars and faint dust, you're staring into a kind of glare, a bright, noisy, high-energy fog created by your own motion. You still have to pick out tiny, dark, fast-moving rocks and denser dust pockets in that glare, far enough ahead that you can react in time. At 0.1 C, your ship is covering 30,000 kilometers, about 18,600 miles, every second. If you want even a minute to respond to a threat ahead, you need to detect it at least 1.8 million kilometers out, more than 4 times the Earth-Moon distance, as a tiny speck against a bright, distorted background. You can try to mount sensors on booms out in front of the main shield and to get a clearer view, but those sensors then sit in the most dangerous zone with minimal protection from dust and plasma. If you tuck them behind the shield, they stare through whatever distortion and scattering that shield and the surrounding fields create. One way or another, your ability to see ahead gets worse as you go faster, at the exact time when your margin for error in timing and pointing is shrinking. And even if you somehow get the navigation and sensing perfect, there's still a simple, brutal fact. One decent-sized rock in the wrong place ends the whole story. Micrometeoroids are already bad. They sandblast your shield, damage radiators, and feed vibrations into the structure. But a rock just a centimetre across, hitting at 1/10 of light speed, carries energy comparable to a small bomb. The matter in that rock and the part of your hull it hits vaporize into a burst of plasma that behaves like a tiny nuclear-like explosion at the impact site. A rock a metre across, about 3 feet, is not survivable for any realistic starship. The energy released at impact is in the same league as large nuclear weapons, focused into your nose and the structure behind it. You can argue that such rocks are rare in any given cubic kilometre of interstellar space, and that's probably true. But your ship's path length is not 1 kilometre, it's tens of trillions of kilometres over a multiple light-year voyage. Your effective swept volume, ship cross-section times distance, is huge. Multiply a tiny number density by an enormous path length, and you get a non-zero chance of hitting something big enough to kill you. You can try to push that probability down with better surveys, better models, and better shielding, but you will struggle to push it to literally zero. So navigation is not just hit the target, it's hit the target while not hitting anything else, for decades, with degrading hardware, tight fuel margins, shrinking sensor clarity, and a constantly moving, partially unknown environment. Every extra year you spend in flight is another year for errors to accumulate, materials to age, and random chance to line up that one fatal collision. Looking at that, you might be tempted to say, then the answer is obvious. Don't spend decades in flight. Go faster, push closer to light speed, let time dilation help the crew, and spend less time in danger. But the moment you try to do that, you run straight into the next final layer of constraint. Relativity itself steps in, and the cost of that extra speed in energy, in radiation, and in weapon-level kinetic impact doesn't just go up, it explodes. Pushing closer to light speed looks like a cheat code. Time on the ship slows down, the crew experiences a shorter trip, and all those decades of dust, radiation, and boredom get squeezed. But relativity doesn't give you that for free. It only gives you time dilation after you pay a massive, upfront energy bill that makes everything you've heard so far look small. Look at 0.9 C, 90% of light speed, around 270,000 kilometers per second, about 168,000 miles per second. At that speed, relativistic effects really kick in. The time dilation factor, the gamma, is a bit over 2. That means for every 10 years that pass on Earth, the crew might feel only around 4 or 5. Sounds great for them. But to get a 1,000-ton ship 1,000,000 kilograms up to 0.9 C, the kinetic energy you have to give it jumps to roughly 10 to the 21 joules and beyond. That's more than twice the already absurd energy we talked about for 0.1 C. Time dilation is not a gift, it's a receipt. It tells you how hard you hit the universe with your propulsion system. So you might think, oh fine, don't go all the way to 0.9 C, just go a bit faster than 0.1 C, split the difference. The problem is, as you keep nudging speed upward, the energy curve doesn't climb in a straight line. It bends up, then it goes almost vertical, At low speeds, kinetic energy goes with speed squared. Double the speed, 4 times the energy. But once you're at a noticeable fraction of light speed, relativity adds another factor on top of that. Go from 0.1 c to 0.2 c, you get more than 4 times the kinetic energy, because the relativistic correction has already started to matter. Go from 0.5 c to 0.9 c, and the extra energy you need doesn't just double. It explodes by large factors for relatively modest cuts in travel time. The closer your speed gets to light, the harder each extra percent becomes. Just go a bit faster quietly turns into build a power system on the scale of a serious fraction of your entire civilization's output and fire it for years. You're trading decades in flight for decades of planet-scale energy production and absurd infrastructure. And all the while, the environment around your ship is turning nastier in a way you can't turn off. At those relativistic speeds, the universe around you isn't the same universe you see from Earth. Even the harmless background starts attacking you. Everywhere in space there's the cosmic microwave background, radiation left over from the early universe at about 2.7 Kelvin. In our rest frame it's soft microwave light, completely harmless, but if you slam through it at a large fraction of the light speed, the background in front of you gets blue shifted. Those photons gain energy in your frame. At very high gamma, what was microwave in the rest frame can become radio, visible, ultraviolet, even X-rays or beyond in the ship's frame. Now stack that on top of the starlight dust emission and gas emission you're also ploughing into. Your forward direction becomes a radiation storm. The faster you go, the more the universe itself turns into a head-on beam of higher energy photons and particles. Your shielding has to handle not only the dust and hydrogen you're physically hitting, but also the boosted electromagnetic background. Your nice dark sky in front becomes a bright hostile glare that your armour and radiators have to swallow and re-radiate without failing. So you might look for a loophole. If straightforward acceleration is too expensive and too dangerous, maybe you can cheat. Maybe there's a way around momentum and energy, something like warp drives or wormholes that sidestep the whole problem. Physics doesn't give you that off-ramp, at least not with anything we actually know how to build. Conservation of momentum is stubborn. If you accelerate a ship by throwing mass out the back, you pay in propellant and in energy. If you accelerate it with an external beam, you pay with massive infrastructure and energy at the source, and you still have to send momentum somewhere, in beams or reaction masses. There's no free push that moves you without something else being pushed the other way. The exotic ideas people bring up, warp bubbles and traversable wormholes, don't get around this in a practical way. The published concepts almost always require forms of matter with negative energy density, something we have never observed, and that our best quantum field theories heavily restrict. Even if tiny amounts can exist in special quantum setups, scaling that to macroscopic Starship-sized structures is far beyond anything we can point to in real physics. It's not engineering hard, it's we don't know if the needed stuff can exist at all hard, so you're left with the basic ugly conclusion. Any real buildable relativistic ship has to pay its debts in ordinary mass, energy and momentum. And once you accept that, a new kind of problem appears on top of all the engineering nightmares. A ship that fast isn't just hard to build. It's automatically one of the most dangerous objects your civilization could possibly create. Take that same 1,000-ton ship and only push it to half the speed of light, 0.5 c, around 150,000 kilometers per second, about 93,000 miles per second. The kinetic energy now sits around 10 to the 21 to 10 to the 22 joules, in the rough range of 100 times the impact energy of the asteroid that helped wipe out the dinosaurs. That's not science fiction drama. That's just multiplying mass by speed and comparing to known events in Earth's history. That means any substantial relativistic ship is, by definition, a doomsday device. A navigation failure, a software bug, a mutiny, or a deliberate attack can redirect that kinetic energy into a planet, a moon, a station, or a habitat. You don't need warheads. The ship itself, just by moving, carries enough energy to sterilize worlds. Even a near miss, dumping that energy into a star's outer atmosphere or a planet's magnetosphere, could have unpredictable, destructive consequences. So a civilization that can launch these things has to solve not just engineering problems, but terrifying security problems. Who gets access to starships that can erase worlds? How do you guarantee that every captain, every AI, every control link stays safe and sane for the entire mission? How do you defend against someone deciding that crashing a ship is easier than maintaining it? Physics doesn't just fight your designs with dust, radiation, and energy curves. It hands you a weapon every time you succeed. By this point, every solution you tried to use to escape one limit has shoved you headfirst into another. Armor fights dust but explodes mass. Shields fight radiation but breed secondary radiation and add even more mass. Higher speed reduces time in flight but detonates your energy budget and turns background light into radiation. The rocket equation crushes any plan that carries its own fuel. Structures shake themselves apart, systems age, biology decays, navigation and security risks blow up with speed. What you're really left with is not one fatal flaw, but a stack of them, each one amplifying the others. And when you multiply their probabilities together over decades, the chance that a cinematic, steel-hulled, human-crewed starship crosses interstellar space and comes out intact on the other side doesn't just drop, it collapses. Put all of this together, and the picture stops looking hard and starts looking broken. Any one of the big problems you've heard about, by itself, would be a monster research project for generations. But interstellar travel doesn't give you by itself. It hits you with everything at once on the same ship. Start with just one constraint. Dust impacts at 1/10 of light speed. That alone demands meters of shielding, hypervelocity impact research, new materials, new structural designs. Radiation alone is another full-blown field, from galactic cosmic rays to solar storms to secondary particle showers in your own shielding. Waste heat alone is a nightmare, gigawatt-level radiator farms that have to stay intact for decades. The rocket equation alone kills almost every fuel-carrying rocket concept before you leave your own star. And that's before biology, long-term repair, navigation, relativity, and security even enter the discussion. None of these are speculative. They're not based on, maybe aliens will do X. They're extensions of lab shots into metal plates, radiation readings from real probes, thermodynamics we use in power plants, relativity we've confirmed in particle accelerators and GPS. You're not wrestling with a single dragon that you can stab with one clever trick. You're standing in a nest of them, and each one gets angrier when you hit the others. The worst part is that when you actually try to design a full ship, the problems don't cancel, they multiply. Armor can help with dust, but the moment you add serious armor, your mass explodes, your engines need more thrust, your propellant needs go up, and your radiators have to throw away more waste heat. Heavy radiation shielding protects your crew, but it also means more material to get hit by cosmic rays, which means more secondary particles spraying around inside, and more structural load to carry around the spin ring and main spine. Try to shorten mission time by going faster, and every dust grain's energy goes up with the square of speed. Interstellar hydrogen becomes a particle beam, and the cosmic microwave background in front of you shifts toward more damaging wavelengths. Slow down to ease impacts and radiation dose per year, and you spend more years in deep space, so the total dose over the mission goes back up, and the probability that something breaks climbs. Push for lighter structures to save mass, and that they flex more, crack more, and are less able to take random kicks from impacts and thermal cycles. You tune one subsystem, 2 others get worse. You make radiators tougher. They get heavier, so thrust and heat go up again. You beef up structure, mass shoots up, and the rocket equation punishes you. The more real constraints you stack onto the same design, the less room you have to maneuver. The nice wide design space you might have imagined shrinks down to a tiny twisted corner where nothing actually works for long enough. And even if you somehow, on the paper, satisfy every requirement once, you still have to ask, what are the odds all these subsystems actually make it through the whole mission together? Take a generous view. Suppose each major subsystem of your ship, propulsion, power, structure, lifeguard support, navigation, shielding, radiators, computers, manufacturing, and so on, has a 90% chance of working well enough from launch to arrival. That's already wildly optimistic over 50 to 100 years. If you have, say, 20 of these big subsystems in series, your overall mission success chance is 0.9 multiplied by itself 20 times. That drops you to barely more than 10%. 9 out of 10 ships fail somewhere, even under rosy assumptions. Realistically, many of those subsystems would be lucky to have a 50 to 70% chance of surviving the full timeline without a mission-killing fault. Multiply a bunch of 0.6 and 0.7 probabilities together, and the total success probability crashes towards 0. And that's before you even factor in unknown unknowns, design flaws you only discover in year 30, human errors, software bugs, or freak-evner. Long missions punish reliability in a way nothing else does. The clock is always running, and probability always pushes more and more of your fleet into the something broke column. So you might ask, what if we get major breakthroughs? Doesn't that change the game? New physics helps, but notice what would actually need to change. You'd want materials that don't creep, crack, or outgas over a century in vacuum and radiation. Superconductors that run at high temperature, never quench, and don't degrade, so your magnetic fields and power systems stay stable. Biology that shrugs off ionizing radiation and long-term low-gravity exposure. Fusion engines that are compact, safe, and nearly lossless, pouring out power without gigantic radiators. Maybe new kinds of computing hardware that don't care about particle hits. Even if you get all of that, the basic structure of the problem is still there. Kinetic energy at relativistic speed still grows faster than linearly. Dust and gas in the interstellar medium still exist, and their impact energy still scales with the square of your speed. Conservation of momentum still demands that if you accelerate a massive object, you pay for it in fuel, beam power, or infrastructure somewhere. Entropy still guarantees that complex systems drift and decay over long enough timescales, and exotic shortcuts like stable warp bubbles and traversable wormholes still require forms of matter and energy that our current theories either heavily restrict or don't allow in the amounts you'd need. To make a routine, survivable, crude, relativistic starship a normal piece of technology, you're not just asking for better engineering, you're almost asking for a rewrite of some of these basic constraints, or for access to physical effects that behave in ways our tested theories say they shouldn't. So when you hear it's impossible to build a starship that can survive interstellar travel, in this context it doesn't mean nothing will ever leave the solar system. It means not the way popular culture shows it, not with steel hulls, glass windows, human crews, and reasonable trip times, using physics and technology even loosely connected to what we know. With today's understanding, and even with very generous speculation about better materials, better engines, and better automation, that the galaxy is not just far away, it is actively hostile to long-lived, crude, high-speed ships. You can still send probes, small hardened robots that take centuries, or wafer-thin sails pushed briefly by huge beams, or one-shot sacrificial craft that don't have to come home. You can imagine wild future tech that bends space-time in ways we barely understand on paper. But the cinematic Starship, the big metal self-contained vessel that launches from one star, crosses interstellar space at a good fraction of light speed, keeps a human crew alive and sane for the whole journey, and then arrives in good enough shape to turn around and do it again. That picture doesn't die because of one show-stopping flaw. It dies because every level of physics, from individual atoms slamming into your hull to the motion of stars in the galaxy, stacks up against it, and the combined odds of beating all of that at once collapse to effectively zero. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.